Welcome everyone. Professor Rosenthal here, and today we're going to explore the concept of linear approximations using differentials. In this lesson, I will try to highlight the following concepts. So, first of all, how the differential of a function can be used to estimate the change in the value of a function. And we'll then try to go over how the tangent line can be used to make estimations. Basically, the number one and number two are very, very much connected. Differential is really nothing but using tangent line estimations to estimate the change in the value of a function. And then we're going to look at two types of examples. One is determining function values near a well-known point. For example, if you know the square root of 100, can you then estimate the square root of 99.6? 99.6 is very near 100. You do a small incremental change in x. How does it change in the value of the function? And then second, we're going to do the types of examples where we are estimating the change in a function when the x value changes slightly. So for example, how does the volume of a spherical ball change if there's an error in measurement for the radius by, let's say, plus or minus 0.02 inches? Then how does it affect the volume? So as you can see, that could have a good application in engineering. So let's get started. So first we're going to look at the theory a little bit and develop the formulas. All right. So here I have a lot of things, but I try to hide not to overwhelm you at first. Let's just concentrate at the moment on the graph, which is at the right-hand side. And in blue you have the function f of x. Let's see. I'm going to just highlight the graph. All right. So we have the function f of x. Now, we are going to look at the tangent line of this function at the point x. Later on, I'm going to refer to this point as x sub 0, a specific point x. And so we have the tangent line given in red. And we move a little bit away from the point x to x plus delta x. So we've stepped aside a unit of delta x in the x direction. The question is, how much has the function changed? So if you are at the point x or x sub 0, the height at that point would be right here. The height would be f of x, right? So whatever the y coordinate there is, so that would be f of x. And what about the y coordinate when you move a little bit away, when you go to x plus delta x? So at that point, the y coordinate will be whatever the y coordinate here is along the function. So that will be our f of x plus delta x. So the function changed this much in reality. When we move from here on the x to here, f of x changed this much, right? So that is your delta y. That is how much the function has actually changed. That's your delta y. Okay. But we are going to use the tangent line approximation. Therefore, we're going to figure out, we're going to estimate this distance by seeing how much the function, not the function, but how much the tangent line changed. So we're going to see how much we have differed from this y coordinate along the tangent line. So that is your dy, or the differential of y. Okay, so let me try to make a few notes on that graph right now, explaining what I just went over. Excuse me, I'm having some technical issues here. Give me one moment, please. Okay, so this point right here is our f of x. And this point is f of x plus delta x. And typically we're going to want to know how much did the function change when x went from x to x plus delta x. So that change will be this distance, right? So we want to know, and that distance is delta y. But we sometimes don't have access to delta y, so we want to estimate that. And the way we're going to estimate it is using the tangent line approximation. So we're going to estimate it by a quantity called dy. And dy is how much we have moved from the original y coordinate along the tangent line. So when you move from x to x plus delta x along the x-axis, how much did your y values move along the tangent line? So that moved this much. So from here to here. Along the tangent line, we move that much. So this is your dy, as indicated over here. And so dy is going to be used to estimate delta y. So dy over here, delta y over there. Delta y is how much the actual function moved in the y direction when you went from x to x plus delta x. Dy is how much the tangent line moved in the x direction when you went from x to delta x. And something to notice here is that we're not going to say, we're going to assume that dx and delta x are the same. So there's no difference between them. However, dy and delta y, they are not the same. And typically dy is a tangent line approximation for the change in y, and that's typically used to estimate delta y. So let's go over a few things that we just pointed out on the graph. So delta y is how much you've changed, how much the function has changed when we go from x to x plus delta x. Dy is how much the tangent line has changed. And as an equation, what would that be? Well, the slope of the tangent line is the derivative f prime of x. That tells you the unit change in y per unit change in x. So if you go this many units in the x direction, and the slope is f prime of x, so how much have you moved in the y direction? So take the slope and multiply it by that incremental change in the x direction. That'll give you the total change in the y direction along the tangent line. So dy, the change in y, is going to be the derivative, which is the slope of that line, is the derivative, right? That's the slope of the tangent line, multiplied by this distance, because slope of the tangent line gives you how the unit change in y per unit change in x. If your unit change in x is this many units, your change in x is this many units, then your change in y will be slope times that. So just a quick reminder. So if your m is delta y over delta x, and if you want to know what delta y is, multiply m times delta x basically. And on the other hand, basically what we have is something like dy over dx is the derivative, which is f prime of x. So if you want to know what dy is, multiply both sides by dx. So dy will be f prime of x times dx. That's another way to think about it. So that's what we have here, and that's the explanation. So we already mentioned delta x and dx we're going to assume are the same, whereas delta y and dy are approximations of one another. And we've also noticed that because dy is this quantity up here, so delta y will be estimated by the tangent line, which is f prime of x times dx. So from there, we can get actually a longer formula. So remember, delta y is the actual change in the value of the function, which is being approximated by this differential f prime of x dx. So if this is equal to delta y and this is equal to delta y, let's just set them equal to one another and have another simple identity there. So the actual change in the function will be estimated by f prime of x dx. And from there, you can add f of x to both sides, and we have this equation. This is sometimes also referred to as the linearization of the function. So f of x plus f prime of x times dx. You're going to see this again in Calculus 2. This is the first degree approximation. There's going to be a second degree term, a third degree term, and so forth when you study the Taylor polynomials. But for now, this is the one we're going to use basically to get an approximation on the tangent line. So one more quick explanation and we're going to the examples. If you know the value of your function at x sub 0, call it f of x sub 0. And if you want to know what happens if you move a little bit away in the x direction, what happened on the tangent line, how much did it rise up? So wherever you were initially, plus whatever this distance is, right? And that distance is the same as slope of the tangent line multiplied by how much you moved in the x direction. It'll be f prime of x sub 0 times delta x or dx. So that's what we have here. Instead of x, I've used x sub 0. So if you like, you could give an x sub 0 there to talk about a specific point. So we're going to refer back to these formulas in the next few examples. All right, starting with approximating the value of 9.2 without using a calculator. So before we do anything here, let's first of all identify the following expressions. What is the function we're dealing with here? That's square root of x function. What is the point where we're going to center our tangent line approximation? That's usually where you know the function pretty well, like we know the square root of 9 pretty well, right? So we're going to center it at 9, so the x sub 0, where we take the tangent line, will be at 9. And with the delta x, you've moved how much away? At 9.2, we have moved 0.2 away. That's our delta x. And what is the derivative of this function? We're going to need that in a little bit in the formula. The derivative of root x is 1 over 2 root x. So we're going to need all of these things as we finish the problem. So what is, we want to know the square root of 9.2. So our delta x is 0.2. What was the formula from the previous page? If you want to know what happens to the function when you move a little bit away from it, first you write down what you know at the center, at that given point x sub 0, and you add to it f prime of x times dx. So in this case, dx or delta x we're using interchangeably, and f prime of x sub 0, so it's going to be centered at 0.2. So this is the formula from the last page, and let's just plug in our values. And for that, I'm going to go to my next slide. So we already know many of these from the last page. All right, so first evaluate the function at 9. So what is the square root of 9? That'll be 3. And then delta x is 0.2 and f prime of x sub 0. So I'm going to plug in 9 into the derivative equation to get this. Square root of 9 is 3. F of 9 is the square root of 9, which will simplify as 3 in the next step. Again, square root of 9 here is 3. You have 1 over 6 times 0.2. So 0.2 divided by 6 plus 3 gives us 3.033. So that is our estimation for the square root of 9.2. And what does the calculator give us for that? And almost the same value. And just know that the further away we go from 9, the worse off this approximation is going to be, because the tangent line is going to deviate from the actual function. So if this is your function, and maybe you do the tangent line right there, so the further away you go from that point and using the tangent line to get the y value, you see that it's getting further and further away from the actual function. But if you move just a tiny little bit away from 9 to 0.2 away, then this is a very good approximation as our comparison shows. All right, one more example of the same type. Could you take the square root of 99.4? This one I'd like for you to do it, and I'll show you the answer momentarily. All right, spoiler alert. If you haven't paused the video, please do so before you take a look at this answer. So our function is still the square root function. The center point, okay, where would you want to center this? A point close to 99.4 where we know the square root. How about 100, right? What about delta x? For this one, we're a little bit below that 100 value. We're 0.6 away, but below. So the increment is negative 0.6. All right, the formula says f of x sub 0 plus f prime of x sub 0 times delta x. And once again, the derivative we already know from the last page. We're centering at 100, so take the square root of 100. Then plug in 100 into here, 1 over 2 times root 100 times delta x, which is negative 0.6. Simplify this as 10, 1 over 20 here, and negative 0.6 multiplied by that. So the square root of 99.4 approximately is equal to this, the sum, which we can simplify as 10 minus 0.6 over 20. And if you do that, you will get 9.97. So not too surprising because we expect it to be less than 10, right? Because square root of 100 was 10. And if you do this on the calculator, you're going to get something pretty close to it once again. To the nearest hundreds, we pretty much got the correct answer. Here's another example for you, this time a cube root. You can use differentials to estimate the value of the cube root of 26. Once again, please take a few moments to do this on your own, and I will briefly go over the solution with you. All right, here it comes. Our function is a cube root function. Where we're going to center it, I would suggest we go with 27. It's a perfect cube near 26, right? The delta x, we're 1 unit below there in our estimated value, so minus 1 is delta x or dx. The derivative of cube root of x, write it as x to the 1/3 and differentiate it. 1/3 x to the power of 1/3 minus 1, which is x to the negative 2/3. And that you can write as follows. Drop it into the denominator, right? Because of the negative power. This is a cube root and the second power. All right, remember the formula. That's f of x plus f prime of x times delta x. At a specific point, x sub 0 is what we're going to do, where we're going to do the estimation. So evaluate the function at x sub 0 or 27. So we're going to do this at a specific value, x sub 0. So cube root of 27 plus the derivative at 27, so plug in 27 in here. 1/3 times 1/3 root of 27 to the second times the delta x, which was minus 1. And when we simplify all of that, we get the following. Three plus 1/27 times negative 1. In other words, 3 minus 1/27. And you can get common denominators, subtract the 1, you will get 80/27 or 2.963 as a decimal. And you should check to see that this is not too far off from the actual value. Let me quickly check it. Cube root of 26. Do I have one of the older calculators here? I don't have a cube root. So when I checked with another calculator, I find this is the value of cube root of 26. And as you can see, it's again very, very close to the nearest thousands. We match the calculator value. Again, the increment was small. If the increment had been larger, this estimation would not have worked as well. That's where in calculus 2, you're going to learn the quadratic term, the third-degree term, and beyond to make the approximations better as you move away from the center point. Now, the other type of example I had mentioned at the introduction was, okay, if you know a quantity changes by a certain value, how much a function that relies on that quantity changes. So, for example, consider a circle of radius 10 inches. If the radius is increased by 0.1 inches, how much do you think the area will change? Also comment on the percentage change. So, we know that the circle has radius 10 and the radius increases by 0.1. What's the impact on the area of the circle? First of all, what is the formula for the area of a circle? Pi r squared. So here the formula, we're going to use only basically the second part of the formula. So delta A can be approximated by dA, which is A prime of r times dr. This was the second part of that formula, A prime of r times dr. And what is A prime? Differentiate this, you get 2 pi r dr. As a matter of fact, I don't need a dr here. Just the derivative is 2 pi r, but then it's going to be multiplied by dr to give us dA. So A prime of r times dr is going to be placed right here. So the differential of the area function, which approximates the change in area, equals the derivative, which is 2 pi r times dr, since we're only moving away by 0.1 inches, so that's our change in r. And we're going to evaluate this when the radius is 10, because we're doing this for a circle of radius 10 units. That's important to know because if you have a very, very small circle, if you move just a tiny bit, area is not going to change that much, right? But if you have a huge circle, even if the radius moves just a tiny bit, the area is going to change a lot. So what the radius is at the given moment matters in terms of how much the area will change. So here the radius was 10, so we plug that in, and there we're going to have our estimate. 2 pi times 10, 20 pi. But don't forget the times 0.1, so 20 pi times 0.1 gives me 2 pi. And as a decimal, I get 6.28 square inches roughly. Square inches because units for areas in square inches and change in area will also be in square inches. And what about percentage change? For that, you need to know change over the total area, so dA over A. We already know dA. Now, you could do this numerically, but you can also do it by putting the actual quantities like 2 pi r dr over pi r squared and simplify it that way. Okay, but here I'm just using the numerical values for dA and A. The pi's cancel, and this is what we get. 0.02. So as a percent, that's 2%. So when the radius changes by 0.1, goes up by 0.1, area at that moment in time is going to change by 2%. There is actually a way to do this without derivatives. You could find the area at 10.1 minus area at 10 to see when you go from radius from 10 to 10.1, how much does the area change? Now, it's good to do it by checking, but typically for these questions, I'm going to ask to see to show the work using differentials because there's higher level problems where this checking is not possible. So that's the whole purpose here for you to understand how to do these problems with the differentials approach. But whenever you can check, it's always a good idea. Since area is pi r squared, I'm doing pi times 10.1 squared minus pi times 10 squared to see how close did we get in our answer. 6.31 square inches versus 6.28. So as you can see, it's a very good approximation. All right, it's now time for one more problem. Let's do this one. Use differentials to approximate the increase in the surface area of a sphere when the radius increases from 4 to 4.1. So please take a few moments and then we'll discuss the solution. And you will need to know the surface area of a sphere in case you don't remember it. It is 4 pi r squared. So spoiler alert, solution is about to show up. So hopefully you got a chance to think about this before you look at the final answer. So our function is the surface area function. 4 pi r squared. Its derivative is 8 pi r. Delta S approximated by ds is S prime of r times dr. So 8 pi r dr. And this is happening at the moment when r is 4 and the change in radius is 0.1 inches. Let's multiply them together to get an estimate for change in surface area, 10.05. How do you find the actual value to see how close we got? Find the surface area at 4.1, subtract it from the surface area at 4. And that turns out to be relatively close, but not extremely close because surface area is a very, same thing with volume, you know, it's the quantities are much bigger, even a tiny little bit change makes a bigger change. So our estimate is not as close as the one last example, but it's still not too bad. And I went ahead to double check that. I noticed I had a little typo here that I forgot to square, but on the calculator I already had that, so I got the same answer. So again, it's slightly more than expected. But you know, if I got something like 15 or 25, the purpose of doing the second part is to show that, you know, the answer should be relatively close. It's not going to be always super exactly the same value, but you should be suspicious if these two answers differ quite a bit. So you should go back and check your result. At least it'll give you an idea about if your answer is correct or not. All right, your last example is on the screen, and this one I'm just going to give you the final solution. So this is a good time to pause the video. So we're dealing with a cube this time. The volume formula is if one side is x, volume is x to the third. At the moment when the edge is 15 inches, if there's a possible error of 0.03, what will be the propagated error for the volume of the cube? So we want to know delta V, which will approximate by dV when x is 15 and delta x is 0.03. So using the same formula as before, dV is V prime of x times dx, which is 3x squared times dx. Now here I'm using plus or minus notation because we're dealing with the error. We don't know if it's plus or minus 0.03 inches. So to be on the safe side, when we hear error, we're going to use plus or minus notation. The derivative was 3x squared, and evaluate this at x equals 15, and multiply the numbers. So we get the change in volume. We estimate it to be 20.25. In case you want to check the actual value, do the volume at 15.03 minus the volume at 15 to see the impact when x goes from x to plus or minus 0.03. So volume formula is simply cube the number. And again, not too far off, 20.29 versus 20.25. And this calculation is not that helpful when you're determining the percentage error in the formula, like when you want to leave it in the variable notation. So the differential notation would be better then. Let's figure out the percent error. That would be dV over V. dV we got above. V at 15 is 15 to the third power. And the simplified answer is roughly plus or minus 0.6%. So not too bad, less than 1% change in the error, but notice of course that x was changing very, very slightly, only 0.03. But I just want to show you one last thing as we end this segment, and that is when you are doing dV over V, you don't have to go to the original values. You can actually use the formula. So dV is V prime of x, right? V prime of x times dx, which is 3x squared times dx. And V was x to the third. So you will see some simplifications here, like x to the second over x to the third is 1 over x. So you're going to have 3 times dx over x. And at this point, you could plug the values in. So dx is 0.03 and x is 15. And from here, you could get the same answer, 0.09 over 15. And double check to make sure that that too will give you 0.006. So I just checked it, indeed it is 0.006, and I added my plus or minus because in our case dx is a propagated error which can be represented as plus or minus. So the advantage of doing it in the second approach here is like sometimes you have a pi in the formula, the pi's are going to cancel. So this sometimes gives a much more cleaner, crisp answer. And in some situations, they may actually want to know the answer as a variable. So the second approach sometimes will simplify greatly to give you a very simple formula for the percentage error. So I hope that this video helped you understand a little bit more about differentials and tangent line approximations, and hopefully you can do a good number of examples now to practice this concept. See you next time.